Hello everyone, I am Priyanka studying an 8th SEM Computer Science course from Ra Bahadur Y. Mahaballeshwarappa Engineering College. Here I am to give you a brief description about real-time secure health surveillance for smarter health communities under the guidance of Lingaraj K. Sir. Let us move forward and have a look at the agenda for seminar. First, we will understand what it is all about. Then, we will see about introduction and what are the main objectives and areas where it can be implemented. Later on, let's discuss on various components of a system architecture and understand what exactly it is all about. Then, let's focus on the exact protocol to be followed and what's the end result of it. And then applications, and finally let's conclude with a conclusion at the end. So we will discuss each of them in detail. Let's look at the abstract of overall seminar. Pervasive healthcare services with smart decision making capability and ubiquitous communication technologies can forge future smart communities. Let me just rephrase it. It is that due to widespread of healthcare services, we can build a smarter communities by making decisions smart and with the help of 4G or 5G networks available. In addition, a real-time health surveillance can easily detect life-threatening diseases through advanced sensing and communication technology, which will lead us to provide better treatment, reduce medical expenses, and save lives of community residents. Once we get information about a particular state of a patient, the assurance of the data privacy is the prime concern for such smart health technologies. Certainly, we need to describe a privacy preserving cloud-based system for real-time health surveillance through change detection of multiple vital health signs of smart community members. And in the final, the development of a predictive model for the smart community considering the sensitivity of data processing in a third-party environment. So in order to proliferate future smart communities, we consider a parallel approach for encrypted computations using a MapReduce algorithm of Apache Hadoop. So let's move forward and look at introduction. In the first place, a secure pervasive healthcare application utilizing wearable sensors, cloud computing and Internet of Things, all these can expedite the evolution of future smart communities. In addition, the adoption of secure and effective techniques for the early discovery of life-threatening disease in real time can minimize the dependency on caregivers and reduce healthcare costs. Furthermore, the innovation of smart decision-making techniques can enable early treatment, thus resulting in favorable health outcomes and potentially saving lives in the community. So, in order to achieve all such goals, we need to continuously monitor the vital signs of community residents, which can be captured through wearable sensors, and it is compulsory. Well, it is required. All the healthcare providers then can provide efficient remote healthcare communication for monitoring and diagnosis services to the residents of these smart communities. So this slide tells you about the various objectives to be considered, and they are in regard to develop a secure health surveillance system for smarter health communities. In addition, to detect anomalous changes in multiple vital signs of community residents. Thirdly, for storing, managing and processing a massive amount of patient data. Furthermore, to consider protecting confidential data and to develop a privacy preserving and cloud-based prediction and abnormality detection system based on FHE for smart communities. More importantly, to develop a secure and smart decision making technique using Hall's linear trend method. Besides, to design a parallel algorithm of Hall's method to improve the efficiency of encrypted data computations. Now let's just focus on the area of interest, big data, where a sufficient amount of data is present. IoT, Internet of Things, where things get smarter when connected to internet. Cloud computing, a platform to store, manage and process the data. Now let's focus on various components of a system architecture and its core functions. So this figure illustrates the architecture of privacy preserving health surveillance system for the smarter community. Multiple vital signs of different community members are captured and sent to the cloud using a smartphone as a gateway. So as shown in the figure, where smart community people will provide the information about their health status, and this is fetched by the phones, and phone will provide the information to the cloud. The most commonly monitored vital signs and the medical terminology indicating a change in status includes heart rate, respiratory rate, body temperature, fever and hypothermia, and also blood glucose. Therefore, in order to identify the early signs of various clinical deterioration and treatment effects, capturing the abnormal changes and their trends is very essential. So in this architecture, residents of the smart community include patients in the hospital, elderly people in an ambient assisted living environment, and healthy people in smart homes who are concerned about their health. These are all part of smart community, and these are specified on the extreme left of the figure. The caregivers such as hospitals, doctors and nurses who support the remote monitoring of all types of patients and maintain ubiquitous communication in the event of danger are also the part of smart community, and it is on the extreme right of the figure, and it is labeled as smart community. However, in such cloud-based monitoring systems, users are greatly concerned about the privacy of their physiological data and are reluctant to share personal information until a firm assurance in the entire methodology is provided. The architecture shows how our health surveillance system monitors the increasing and decreasing trends, which is very vital signs which should be considered as seriously anomalies. Such trends are computed using a secure mathematical model in the cloud, and smart decisions such as example for notifications which are sent to the health professionals upon detection of such trends. In this figure, the increasing and decreasing trends are shown on the top with a graph. So moving forward, this figure illustrates a system architecture showing different components of proposed privacy preserving changing detection and abnormality prediction model in the cloud. So SRM, Smart Community Resident, is a patient whose various factors are monitored such as heart rate, blood pressure, temperature. After collecting the status of the patient condition, this information is encrypted. All this encrypted data is sent directly to the cloud storage. This cloud storage solemn purpose is just to store the encrypted user's data. Smart prediction model is where it works on encrypted data, and mathematical computations are performed based on homomorphic encryption. So the encrypted data is then exchanged between the SPM and AHP authorized healthcare provider for notification and emergency purposes. So next we will come across methodology. It can be explained in three sub portions, and it is as follows. Firstly, fully homomorphic encryption FHE. Second, smart prediction model. Third, improving efficiency by parallel exponential smoothing. Let's take the first one, fully homomorphic encryption FHE. So FHE as a security mechanism in our framework to address two main goals. Firstly, to achieve end-to-end security, which ensures the privacy of patient data while it is stored in the public cloud storage. Secondly, to provide encrypted base processing, which is the monitoring and predictive mathematical computation that is entirely performed while the patient data is encrypted. Here we consider BGV, a well-known FHE scheme, and it is classified as a asymmetric encryption, the security of which is linked to the difficulty of ring learning with the error problem. The basic BGV operations can be distributed as follows. The first operation indicates the key generation algorithm has three inputs, a prime number queue that defines a plain text space and a security parameter L lambda and the depth level of the evaluated arithmetic circuit L lambda. So here the depth level is represented by sigma S. The outputs are a secret key Sk and a corresponding public key Pk. Second operation indicates the encryption algorithm that has two inputs, the public key Pk and the plain text message M. The output is a ciphertext C that is homomorphically encrypted. The third operation is the decryption algorithm that has two inputs, the secret key Sk and the ciphertext message C. The output is a plain text M. So the fact that the BGV scheme has a homomorphic encryption technique is due to the operation OP, where OP is nothing but an operand where it takes an unlimited number of either addition, subtraction or multiplication operations. To sum it all, BGV scheme is built in order to provide a computationally feasible implementations in addition to certain convenience routines on top of the basic arithmetic operations. Here comes the next one, smart prediction model. The real-time monitoring of a vital sign generates time series data that is represented as a sequence of observations such as HR and BP time series data. HR is nothing but heart rate and BP is nothing but the blood pressure. Then we developed a privacy preserving prediction model based on Hall's linear trend method that is an extension of the simple exponential smoothing technique. Hall's method is utilized for time series analysis to forecast future values of vital signs from the available data set. This method involves one forecast function and two smoothing functions. So we require two smoothing functions, one for the level and one for the trend. The level function is given as follows, which is a mixture of the current value with the previous calculated value offset by the trend. So the trend function is given as follows, which is a mixture of the changes in the level function over the most recent time step offset by the previous weighted trend value. The forecast function is as follows, which is the level value summed with the predicted step value based on the most recent trend. So here it denotes LT denotes an estimate of series level at time t, BT denotes an estimate of the trend or slope of the series at time t. A is nothing but alpha, the smoothing parameter for the level, and B is the smoothing parameter for the trend. So it ranges between 0 and 1. And at last, let's discuss improving efficiency by parallel exponential smoothing. The figure shown in the slide illustrates the structure of a parallel computations for a set consisting of 30 observations among 5 virtual machines on Google Cloud Platform using Hadoop MapReduce model in order to increase the computational speed and efficiency. The results in the table are derived by executing different functions of Hall's linear trend method in the encrypted domain. Let us look at the results after following the three methodologies. So, this chart represents change detection of different vital sign values based on our privacy preserving monitoring and prediction model. These are the various graphs based on various factors like temperature, glucose level, heart rate level and so on. Next, this table gives the performance of monitoring and prediction model with varying number of collected observations based on both sequential and parallel. Here we can observe that by executing parallel, the computation time is very minute compared to sequential. The coming table tells about the error rate of parallel prediction model with varying number of collected observations and size of subsets. Let's move forward by discussing about applications. Real-time health surveillance for early detection of life-threatening diseases. Through advanced sensing and communication technologies, we can provide a better treatment, reduce medical expenses and save the lives of community residents. Conclusion at the last. So, in conclusion, modern surveillance technology is continuously improving pervasive healthcare in smart communities. However, the privacy of community residents' data is an obstacle. More importantly, implemented a privacy preserving and cloud-based smart prediction model based on fully homomorphic encryption. Developed a secured forecasting technique using a Hall's linear trend method for predicting abnormal changes in patients' vital signs by detecting a trend which can predict the growth of several chronic diseases. So, thus in all, the framework functions in a completely independent manner and all analysis computations are carried out on encrypted data. The analysis results can be retrieved by data owners through the cloud service provider. Finally, developed an innovative parallel approach of Hall's method to significantly improve the efficiency of FHE computations. At the end, these are the various references to go through, and thank you.